If you energize a high-voltage transformer before proving its internal integrity, the grid's raw power will find the weakest path to ground. A catastrophic fault tears through the copper windings in milliseconds, destroying equipment and threatening lives. To prevent this, engineers execute a rigid, 5-stage commissioning sequence. This is a progressive series of diagnostic tests designed to systematically prove the physical boundaries and electromagnetic behavior of a voltage transformer, or VT, before it ever sees grid power. Every step of this process is dictated by overlapping global standards from organizations like the IEC, IEEE, and NEMA. Because these codes occasionally conflict, operators follow a strict reference governance rule. If a project specification, a manufacturer's manual, and a global standard demand different testing parameters, the engineer must identify and apply the single most stringent requirement among them. VT commissioning serves as a rigorous, legally binding audit of grid safety, requiring precise verification to move forward. Before any diagnostic probes are attached, the absolute baseline condition must be established. The VT must be explicitly de-energized and proven completely dead. The unit is then physically isolated from all secondary circuits. Every connected burden, link, and fuse is removed. This isolation prevents secondary backfeed. If test signals travel downstream into connected metering equipment or protection relays, those devices could inadvertently step the voltage back up, electrifying the immediate workspace. Once the environment is secure, operators connect the primary diagnostic engine for these procedures, the Omicron CPC-100 multifunction test set. Failing to properly verify this zero-energy isolated state introduces immediate lethal risk to the operator and permanently invalidates all subsequent test data. The technical sequence begins by proving the dielectric barriers. We need to verify the insulation separating the primary windings, the secondary windings, and the ground boundary before any functional voltages are applied. As this schematic shows, operators first test the primary to ground boundary by injecting a direct current of 1,000 volts. Next, connections are shifted to measure the primary to secondary boundary at 500 volts DC. Finally, the secondary to ground boundary is tested, again at 500 volts DC. For each of these 3 phases, the voltage must be applied for a continuous 60 seconds. This duration ensures the capacitive charging currents dissipate, allowing the resistance measurement to perfectly stabilize. Because DC testing essentially turns the transformer into a large capacitor, leaving any terminal charged is highly dangerous. Complete electrical discharge between each measurement phase is a strict safety mandate. With the external dielectric boundaries verified, the focus shifts inward to measure the exact ohmic health of the internal copper windings. Looking at the connection diagram, this requires a 4-wire Kelvin setup. Separating the current injection and voltage measurement leads at the terminals factors out test cable resistance. In the CPC-100 interface, the operator opens the winding resistance test card, entering target DC current and ambient temperature. The system utilizes a formula defined by IEC 6076-1 to mathematically normalize the raw resistance reading. It takes the measured voltage, current, and ambient temperature and outputs a calculated resistance against standard reference temperatures. Because the internal coil of a VT is highly inductive, it resists the sudden flow of direct current. The injection takes significant time to saturate the core and stabilize before a valid reading can be captured. Capturing this precise measurement establishes a thermal baseline. It proves the physical copper path is intact and won't experience thermal runaway when exposed to continuous grid operations. Moving past static DC resistance, the sequence evaluates the transformer's dynamic alternating current behavior, specifically its electromagnetic step-down ratio. This logical schematic illustrates the process. Inject a precision AC voltage into the primary winding while simultaneously measuring the resulting voltage generated on the isolated secondary winding. This interface layout shows the CPC-100 test card, where the operator enters the nameplate ratio parameters and specifies the expected secondary output voltage for the system to track. During the active AC injection phase, operators physically monitor the unit. They listen for abnormal vibrations or noise from the core, while watching the screen for unstable fluctuations in the measurements. Before the injection sequence can start, a mandatory hold point requires a commissioning witness to physically verify that all burden isolation is complete, preventing any unintended power transfer. Validating the exact step-down ratio is critical. Even a fractional deviation here corrupts the primary logic of downline protection relays, feeding them inaccurate data about the grid's actual state. A perfect step-down ratio is useless and highly dangerous if the secondary phase relationship is inverted. As detailed in the test diagram, the system uses a specific polarity check to prove phase direction. The CPC-100 injects an intermittent, sawtooth-style pulse signal directly into the primary terminals. The test card is configured with a strict duty cycle, typically applying the pulse for 2 seconds and then pausing for 9 seconds to allow the secondary response to reset. An operator tests the secondary terminals using a handheld polarity probe. A green LED confirms the signal is perfectly aligned. A red LED immediately flags a reversed or distorted response. Polarity alignment acts as the geographic compass for the power grid. It ensures that protection relays detect faults in the correct direction rather than mistakenly tripping offline during healthy circuit operations. The final major hurdle is the high-voltage withstand test. This diagnostic pushes the dielectric boundaries we verified earlier to their absolute operational limits. This connection diagram shows the withstand configuration, where operators short the winding connections and prepare to apply up to 2 kilovolts of alternating current across the target boundary. The application is tightly controlled. The voltage follows a specific ramp characteristic, rising slowly from 0 to the target limit, holding for the measurement span, and then steadily ramping back down. During the hold span, operators continuously monitor the environment for signs of physical flashovers, complete dielectric breakdown, or abnormal leakage currents crossing the barrier. Because of the massive energy involved, a strict safety protocol demands that a client or commissioning authority witness physically approves the setup before the high-voltage output is ever armed. Passing this final dielectric test without insulation failure physically proves the unit is structurally ready to handle grid-level operational voltages. Flawless execution is the goal, but commissioning engineers must also be prepared to manage extreme hazards when the physics behave unexpectedly. During DC injection, the highly inductive core stores massive amounts of energy. If a measuring circuit is disconnected while current is still flowing, the collapse of the magnetic field generates a lethal voltage transient, known as inductive kickback. To manage this, a strict shutdown protocol is enforced. Operators are forbidden from touching any test leads until the test equipment's discharge LED has completely extinguished, confirming the energy has safely dissipated. Hazards also appear in signal diagnostics. When the polarity probe flashes a red LED, it doesn't strictly mean the wiring is reversed. It indicates a distorted characteristic in the signal wave. A distorted wave forces the engineer to halt the test sequence and hunt for unintended grounding points or parasitic capacitances hidden within the secondary circuit. High-voltage testing creates its own unique risks. During the withstand test, specific secondary terminals, like the 1S1 connection, can carry life-hazardous voltages if inadvertently left connected to downstream electronic relays. Modern test equipment dynamically manages lethal potential energy during the diagnostic process, requiring absolute operational discipline from the engineer. The final challenge often occurs when interpreting the gathered data. Occasionally, a phase-to-phase test deviation might pass the broad limits of the project standard, but fail the tighter specifications set by the original equipment manufacturer. When this happens, the engineer defaults to the reference governance rule. They document the exact discrepancy, but immediately enforce the most stringent standard on the table. Once all tests clear, the final evidence package is compiled. This includes exported test cards, photographs of restored terminal wiring, and the final WIT signature. This exact rigid sequence acts as the ultimate technical filter. It verifies every boundary and ratio, ensuring that a raw mass of copper and steel is fully integrated as a reliable, intelligent node in the electrical grid.